So hopefully you found the slope for the tangent line. The formula is right here, but the explanation of deriving that formula we just went through. I'm hoping that you got something similar to this, right? I liked that they put the condensed version over here as well, just to remind you, remember the slope of anything is the change in y over the change in x, but now we're applying the limit as delta x approaches 0. So in other words, the 2 points gets infinitely close to each other, and therefore it's going to approach the slope of the tangent line at one of those points, the point that we're actually approaching. Some other things to keep in mind: the slope of the tangent line is a lot to say every time. So you could also say it's the slope of the graph at x is equal to c. Because in this case, we're finding the slope of the tangent line at a particular point, c comma f of c. And in the future, it's also, it's one of the definitions for a derivative, so which is our goal. In our next section, that's really what we're going to formally define what a derivative is. So let's take a look. Let's do some examples here. So our job for example 1 is to find the slope of the graph of f of x plus 2 when c is equal to 2 by applying the definition of a slope of a tangent line. Now, it's linear, so hopefully you know that the slope of this line is just 3, but let's actually apply the limit just for practice to prove to ourselves that we're going to get the same answer, even if we use the definition of the slope of a tangent line. So let's try that. So we're going to try that. I'm just going to write down the formula. You do not have to do this every time, but it's good practice just to write it down a couple times, then it kind of sticks in your mind. We have, first of all, the slope of the tangent is equal to the limit as delta x approaches 0 of, sorry, I'm looking down again, f of c plus delta x minus f of c over delta x. So in other words, we need to find f of c plus delta x and f of c. So let's write those things down. For some reason, some people can do it straight away. You don't have to write them down separately. But for me, c is equal to 2. So essentially, I want to find f of 2 plus delta x, and I also need to find f of 2, like that. So that gives me, that means, by the way, anywhere I see an x, I have to replace it by 2 plus delta x for the one and a 2 in the other one. So we get 3 times 2 plus delta x plus 2, which is, when I simplify this here, I get 6 plus 3 delta x plus 2. And the other one, I get 3 times 2 plus 2, like so. There are multiple ways we could do this. I'm going to go back to the slope of the tangent line. We're going to take the limit as delta, oh, Tim, I mean the limit as delta x approaches 0 of, I could just add and say, okay, it's going to be 6 plus 2 is 8 plus, maybe I'll do that, 8 plus 3 delta x. And then this one, 6 plus 2 is also 8, so that's minus 8 over delta x. So to clarify, this part here is f of 2 plus delta x, and this part here is f of c. Oh, f of 2, sorry, f of 2, like that. So let's simplify a little bit. There's some cancellation. I can cancel the 8s out. So now I have the limit as delta x approaches 0 of 3 delta x over delta x. Currently, it's indeterminate form, but we can cancel out the delta x's. So the delta x's cancel each other out, and I'm left with the limit of delta x approaching 0 of 3. Now, there is no delta x left over to affect the 3, so it is going to be 3, which is what we predicted it would be. Now try b, and I have a twice, so let's change that to a b. Now try part B on your own and see if we get the same thing. You should be getting a -5, but your work should support it. And just make sure you pause, because I'm going to put up the answer as soon as you've unpaused. Well, okay, so here I have my work for part B. Just to show you a slightly different way, I just substituted directly into with f of 1 plus delta x and f of 1. And I didn't even bother. I distributed the -5 here, but I saw that when I distributed that anyways, the negative here, they would cancel out. It just kind of is a stylistic thing. You could combine and simplify, but you don't have to if you realize they cancel out. So if you need to take a screenshot or pause it just to check your work, it doesn't have to be exactly it doesn't have to look exactly like mine. Based on what you know about the slope of the line, does these agree with the definition of the slope of a tangent line? And for us, or based on my work, for sure, it agrees. All right, what happens when it's not linear though? It's done in a similar way, it just has a little more work to it, that's all. So here's part A, it should be, so I'm finding this should be A here, and this should be B here. All right, so we're going to do it in a similar way. We're going to find the slope of the tangent line is equal to the limit as delta x approaches 0. Now I'm interested when C essentially is equal to 1. That's what it's asking for, because I'm given the point for which it happens, right? And after I find the slope of the tangent line here, all I have to do is use the x to help me solve that. If I asked for you to write the equation of a tangent line, now I have a point, and once I've found the slope, I can just write the equation of a line. All right, in this particular case, I'm doing f of 1 plus delta x minus f of 1 over delta x. So again, if you need to write down or write out f, this one is you have to expand, so this may take a little more. We have 1 plus delta x, so that means we have to do 1 plus delta x squared plus 1 plus delta x minus 3. And when I expand that out, I get 1 plus 2 delta x plus delta x squared plus 1 plus delta x minus 3. And I then could combine some of the terms. So let's see the 1s, so that is, and the -3. And there's delta x's here as well. So let's see, we get 3 delta x plus delta x squared minus 1, it seems like. And f of 1 is going to equal 1 squared plus 1 minus 3, which is equal to -1. So putting that back into the limit definition and simplifying a bit, I get 3 delta x plus delta x squared minus 1 minus a -1 over delta x. And what happens is that these two cancel out, because it's -1 minus -1 becomes a +1, so they cancel out. And now we end up with the limit as delta x approaches 0 of, in the numerator, first of all, it's indeterminate form as it stands right now, but in the numerator, I can factor out a delta x. So I get 3 plus delta x here over delta x, like so. And then the delta x's will cancel each other out. So that is going to give me the limit as delta x approaches 0 of 3 plus delta x. And then we apply the limit. So that is going to give me a 3. Now I want you to try the same for part B. I'm going to pause it. Once you unpause it, it's then going to give you the answer on the right. For this one, make sure you have the equal signs in, you have the limit every time until you apply the limit. These are the common mistakes that I see for this type of question. But part B, I got a 4. All right, According to the definition of tangent lines with the slope m, when would the tangent line not exist? I want you to think about that. Well, a rational function doesn't exist, or a rational expression is undefined when the denominator is equal to 0. So when delta x is actually equal to 0, it's problematic. So when there is no delta x there, this will happen. So the only time that you can't produce a delta x is when you have a vertical line. So here, this happens when delta x is equal to 0, because it's in the denominator, right? And what type of line has undefined slopes? Vertical lines. So for vertical lines, by the way, it's undefined because it's infinitely steep. So that means you have some form of infinity when you have vertical lines like that. So we define the following. If that happens, that you end up with a limit that approaches positive or negative infinity, you know that the tangent line then is going to be vertical instead. So in this particular case, the definition for, as long as it's continuous, that is that either if you get positive or negative infinity, you will have a vertical tangent line, if you can think about that. That's because if it's just vertical, there will never be a delta x. The x values are always the same on a vertical line that way. So what types of graphs would have vertical tangent lines? There are a whole bunch of them. One is, for example, like cube root of x. You could have it, for example, in circles. Like if you have circles, they will like graphs of circles on the coordinate plane. They will have vertical ellipses. They're all kinds. So whichever, but a real obvious one is the cube root function. The cube root function looks very similar to the one that's there, but it looks like this, like that. That's a really common one, but we come across them quite often. If you get like I said, a circle on the coordinate plane, they're vertical. It has two vertical asymptotes. No, not asymptotes. Vertical tangents. Okay, that's it for this particular part of section 1.